So just to look at what we're getting into today, I'm just going to share screen here. So there was the request to review the root locus diagrams, right? So we'll go through the principles and we'll work through a couple of examples there. And then after that, I wanted to do a bit more on the Bode diagram plotting. So that comes after this page. And then I also wanted to just follow this logic thread here. So in terms of understanding why encirclement of the -1, 0 point mattered, and in terms of understanding what that meant in terms of the stability of the process, there is a fairly long line of logic that you need to follow. So there are a couple of different steps to constructing the logic for understanding that that encirclement of -1, 0 by G open loop, that does imply instability. So we just want to review that logic as well. So that's what we'll be looking at today. If there are other topics you want to cover, right, I think these three are going to take up all the time. So if there are other topics you want to cover, please email me and we can add that to the next session. Any questions or comments so far? Okay, if not, let's get into it. So we've got here that these are the 6, I'm calling them observations. You can also think of them as sort of principles for drawing your root locus diagrams, right? So we are given some transfer function. So we've got something, there's some open loop transfer function. So it's a function in S. And we want to be able to draw the root locus diagram for that. And we typically call that our Nyquist plot. And just to look at some examples of that. So you've got here in the, you've got this tool that you can use to generate your diagram. So here's an example of a Nyquist plot. And you can ignore these green lines for now. But here we are showing all the roots to the equation 1 plus G open loop equals 0. So G open loop plus 1 equals 0. We are interested in the solutions to that. And typically, the reason that that's a line of things is because there's some hidden parameter behind this G open loop, right? So if you look at this equation, you might think, well, if we solve this equation, there'll just be a couple of values of S that satisfy this equation. Whereas, in fact, when we look here, you can see there's a whole, it looks like a continuum of points. So it's not a continuum of points. This is a locus of points, but each point corresponds to a particular parameter value. So our G open loop, remember, is going to be the product of the process. So there's some process and there's our control function U. So GP and U, and U being our control function, that depends on our choice of controller. So it might be a proportional controller. So U might be in a proportional controller or a proportional integral or a proportional integral derivative. And so behind these choices, there are some parameters. So for a proportional controller, there's the KC or KP. So that's the constant that we use in that controller. And so it's really a question what value of K that we want to use. And so as we vary K, we generate different roots of that equation. So anyway, we'll look at some examples of that, and that will be clearer. But these are the 6 principles. So I had a look in the notes that I put out earlier, and then I modified things slightly. So I think there were just 5 principles there. And then I've added in the 6th one here, which for some reason wasn't there. Yeah, I'll share these notes with you on the Dropbox folder. So anyway, the first principle is that our roots, the plot of those loci, starts when we set the value of kc equals 0. And that as kc goes off to infinity, then the roots tend to the zeros of that function. And that's not all the roots, right? Some of the roots go towards the zeros. And then I'm just going to come back to 3 and 4. And then the rest of the roots. So this covers some of the roots, right? So number 1, we've got the loci are starting at the poles. And usually there are more poles than there are zeros, right? So if you have 3 poles, you might have just 1 0, for example. So you have 3 poles. That means you've got 3 loci starting out when you are plotting this. And out of those 3, you'll be able to figure out where one of those is going, right? So we are talking about drawing lines on our Nyquist plane. And so out of those 3, we'll be able to tell where one of those is going. So one of those will end up at the 0. So there's only 1 0 and 3 poles in this imaginary example. So we know where 1 is going. Then for the other 2, we have available the center of gravity and these angles. So this is how we can figure out where the other poles are going as well. Right, so we've got a starting point and an end point, or multiple starting points and multiple end points. So once more, if you have your transfer function, you have as many loci, so as many curves on this plane as there are poles. Right, remember, poles are the values of s that causes to go to infinity. So you have as many poles, you have as many loci as there are poles. And so they start at the poles and they go off either to a 0. So some of them go off to the 0 and some of them go off to the center of gravity asymptote. Right, so those are the start and end points. So some comments on what happens in between. The complex parts of your loci always appear as complex conjugates. So if you get one curve that's doing something in the imaginary axis, then there will exist another line that does the opposite in terms of the imaginary axis. So it will do the same thing in the real axis, but the opposite in the imaginary. So we'll see that just now. Then this concept of break-in and breakaway points, we'll get to that. Okay, so I'm deriving it fully here. But in fact, maybe let's jump into an example first, and then we'll come back to understanding what we're saying here. So here's an example. So I'm just arbitrarily picking this easy transfer function. So GP 0.5 s over s plus 1 times s plus 2. And so that's the process itself. And then we are considering adding in proportional control. So that's Kp times that. And here we are just substituting for GP. So if we substitute this function for GP here, that's the function that we want to draw our root loci for. And looking at this function, if we just multiply this denominator out, so you've got 1 times this denominator. So there's the denominator sitting up here now. And then of course it disappears from this term. So you're left here with Kp 0.5s. Right, and if you look at this this equation, right? Remember, we want to know where the poles are. So so we want to know the values of S that make this equation true. In other words, what are the solutions of S? So if we look at the special case of k equals 0, right? If this kp is 0, then we can ignore this term. And then we can easily see two solutions. We can see that when s equals -1, then this whole thing becomes a 0. And also when s equals -2, this whole thing also becomes a 0. So those are two solutions. And as we said, the poles are where our loci start. So when we say start, we mean kp is 0. And then as kp increases in value, we are moving further along the curve. So we are generating a curve that varies as we increase kp, right? So that's where it starts. And let's see. We can, of course, multiply this function out. So we can say, okay, that's nice to know that we start at these 2 points. And now we are interested in values besides just kp equals 0. So it's useful also to just multiply this whole thing out, which we do here. So of course, s squared plus 2s plus 1s is 3s, and then the 2 here, and then that term stays. And so we can regroup this, and we can then say, well, this is by the end of the day a quadratic equation, and we can use the usual quadratic formula, and we can solve this equation. So this is now telling us the roots of S. It's telling us the values of S which make this equation true for any value of Kp, right? So we can choose any value of Kp and we can find the two values of S. So that's the most general, that's the most general form of this. And then we can also think about, as Kp goes to infinity, what happens here. So if we let Kp go to infinity, here this term will become much greater than this 3, right? So Kp going off to infinity, this term is much greater in magnitude, so we can simplify this, this factor, and we can just rewrite that without the 3. And then similarly here, this will become much larger than the 3, so that becomes that. And also then this whole factor will become much larger than this 4.2. So we can write it quite simply like this. And so we can say that as Kp goes to infinity, S becomes approximately this. And then this is equal to, so of course that's just minus Kp, and then it's plus minus, it's square root of the square, so it's just that. And so we can see, we can either choose minus 0.5 Kp plus 0.5 Kp, which is a 0, or minus 0.5 Kp, so that's minus 1/2 Kp. So those are the two values of the root as Kp goes to infinity. So we can get the start points and the end points, and then it's a matter of looking at what's happening in between. So as we say, we can generate what's happening in between by writing the equation out like this. So I just want to come back here to the principles for plotting these root locus diagrams. So we said here the root loci start at the poles of the transfer function. So we sort of saw that now, but let's look at justifying it a little better. So here we know that our open loop transfer function can be written as the product of the process and the control function. So if we know that the process is written in terms of its zeros and its poles like this, right? Remember we established this, I think, in the second set of notes. We had shown that our process function is usually written as the product of the values which make that function go to 0. So we identify these as zeros divided by the poles. So the values of S where each of these terms go to 0. In other words, if we've got a 0 in the denominator, then this function goes to infinity. So we call these the poles. right? The pole, it's going off to infinity. So we identify those as poles. So that's U and GP. And then we can say on our root locus diagram, the roots are, we are looking for the roots of this equation. So we can separate this G open loop into the process and the control function. And so we can rewrite it like this. And then we can just multiply this function by the denominator as we did before. So we multiply this denominator by that 1, so that goes up there, and leaving us with kPa times this here. Right, so that's our equation. And so if we set kp equals 0, then all this disappears, leaving us with just this part. And so we can say that the values of s, which make this true, are the values where s equals p1 and s equals p2 and so on. So that's why the poles are where the root is going to start when kp equals 0. Right, so that's, I wouldn't really say proving, but that's sort of justifying why we can make the statement as one of the principles for drawing these diagrams. The second thing we can also say is, well, when kp is going off to infinity, then this term becomes much larger than this one, right? And I think I've done that down here, right? So if kp is going off to infinity, then we can say this term becomes negligibly small in comparison. And so approximately this is all that's left over. So if the equation becomes like this when kp is going off to infinity, then clearly the only solutions here are these z values, right? So as kp goes off to infinity, the solution becomes, they become the poles z. And then when we look at what's happened here, we've got n poles, let's say, and m zeros. Now it's not the case that if we have, let's say, 3 poles and 1 0, that somehow some of those are all going to merge and become one value at the end. The way we understand it is that one of those curves, for one of those curves, we'll know where it's going to end up eventually. And for the other 2, we have to use other methods for figuring that out. And so that's where we have the center of gravity story, right? So the complex number analysts have developed this where it can be shown that as kp goes off to infinity, if you produce those lines, right? Remember, these are all curves. So as kp is going off to infinity, if you look near infinity and you produce that line backwards, right? If you take all those lines, let's say there are 3 loci, and if you look at where they are going off to infinity, if you produce all those lines backward, they will all point back to one point. And that one point can be figured out like this. So our center of gravity is given by the sum of the poles minus the sum of the zeros divided by n minus m. So when we say the sum of the poles, right, the pole is an actual number, right? The pole is not some concept or some method. The pole is a number here, right? In this expression, this is some number. Generally, it can be a complex number. So the pole is some number, and so we add up those poles and we add up those zeros and we subtract these 2, and then we divide by n minus m. And again, that's just the number of poles and the number of zeros. So this is going to give us a number, and so that's going to tell us where all those loci are kind of originating from, where those asymptotes are originating from. So now we have a point, and then we want to know at what angle are we departing from that point? And we use this formula to do that. But of course, as I say, let's do an example of this and come back there. In fact, let's carry on with the same example. Any questions or comments so far? So we've got this development. We know the starting points, -1 and -2, right? And so those are just the poles. We can see that there is going to be a 0. So one of those loci that are originating at those 2 points, one of those is going to go into 0, right? So this is s minus 0. So one of the zeros is 0 there, and then that leaves us with one left over sort of undetermined root. Right, so we can imagine if s starts at -1, so maybe that -1 is going to go back to 0. Then we don't know what that -2 is going to do. We don't know where that line is going to go. So we need to work that out using the center of gravity approach. So let's do that. Let's do that here, and I'm just going to copy the function. And so let's just do that here. So our center of gravity is the sum of the poles minus the sum of the zeros, right? So I'm just going to copy this. So the sum of the poles, and we can see our poles here are simply -1 and -2. So -1 plus -2. Oops. Okay, so I'm just going to write it as -1, -2. And then the 0 here, and we'll write it in explicitly as a 0. And we can see here we have 2 poles and 1 0. All right, so this is -3 over 1. So we can write that as -3. So we have this so-called center of gravity at -3. And then we need to know how the asymptotes look around that -3. So we need the angle as well. So for the angle, we have this formula. And I know you can do it faster than this, but I feel it's a little bit helpful first to just write out the values for k that we are going to loop through. So n minus m, so that's 3 minus 1, so that's 2, and then 2 minus 1 is a 1. So we can say k is going to have the values of 0 and 1. And so we need to generate just two angles here. And so the angle is going to be when we apply, so I'm just going to write here, log equals. And so when k equals 0, then that's a 1 over 2. So that's pi over 2. Pi over 2. So that's the first angle. And then when k equals 1, then that's 2 plus 1 is 3. 2 plus 1 is 3 over 2. So that's 3 over 2 pi. 3 over 2 pi. So those are the two angles. So we seem to have a point at -3, and we have an angle of pi by 2. So of course, pi by 2, if you start from 0, so sorry, I have to work, maybe I need to invert my camera, but if you're pointing along the positive real axis, then pi by 2 is vertically upwards. So you can imagine at the point -3 pointing vertically upwards, and then 3 over 2 pi. So if that's 0, then it's pi by 2, then pi, then 3 over 2 pi. So it seems like at -3, there's a line going up and there's a line going down, right? So
sorry, Joe.
Yes.
For the k values, do we have 1 as well? Because if we're taking that n minus m minus 1, does that not equal just 0? And then we have to stop there.
Well, oh, let's see. So you mean we've got 2 here and 1 there. So
Yeah.
yeah, that's right. There's only 1. There's just a 0. Thanks for that. So once
Okay,
more,
thank you.
yeah. So once more, we've got 2 for n and then 1 for m. So that's already just 1, and then 1 minus 1 is a 0. So k is only equal to 1. Sorry, k is only equal to 0. So we've got just pi by 2. Okay, thanks. So we've got the 1, so we've got at -3 and then pointing straight upwards. So that's how our other asymptote is going. And to kind of validate this, we can just go over to the brute force way of generating this plot. And remember, I wrote this code which will plot any function. So I'm just going to list this function. So we've got here GP equals 0.5 times S over, and it's S plus 1. Plus 1 times S plus 2. That's, oops. I think I just didn't write this function well. So GP, oh, it needs to be a string. Okay, it's running. So it gives you a bit of feedback. It is searching for roots analytically, so you can see what roots it's found there. And again, ignore these green lines. And I'm actually going to reduce my range for KP because this root is kind of dominating the picture. So for KP, let's just restrict that to 5. So we are letting KP vary from 0 to 5. And we are expecting our loci to start at -1 and -2. And one of those roots is going to go to 0. And the other one is going to use that center of gravity style approach. Okay. And yeah, so you start here at -1, 0. So you start at -1, and then you can see that's tending towards 0. And it hasn't made it all the way to 0. That's because I've gone and restricted the range of KP. So as we increase the range for KP, you'll see this end point getting closer and closer to the 0. For the other one, it's actually not pointing in the right direction, or it's not pointing in the direction I said it would, right? We can see it starts at -2, but it's going in this direction, and that's because I hadn't corrected that part, right? After the correction you mentioned, k equals 0. So this is 1 over m minus n. So that's actually a 1, right? So I had thought that was a 3 because of that earlier example I was talking about. Well, I'm not trying to justify here, but this is just pi, right? So if you look at it, this is k is 0. So this is up here is a 1. And then it's actually 2 minus 1. So that's a 1. So it's 1 over 1 times pi. So the argument is pi. So we are pointing in the negative real, or in the negative real direction, and we are starting at -3. So if you look here, that's telling us your asymptote looks like this. So the center of gravity is 3 like this, and it's pointing down that way. And you are starting at -2. So you start at -2 and you move in the direction that that asymptote is pointing. So we'll look at a slightly different example just now to make that point clear. But you first figure out which point belongs to which endpoint. in this case, the -1 was closer to the 0, so that's so this line went off in that direction, and then the other one starts at -2, and it's moving off in this direction, right? So, sorry, 1 second. I'm busy. Okay. Okay. Thank you. I'll be back in a second. Okay.
Is that weird? Isn't it, Daddy?
Okay.
Is that weird? That is so
Yeah, sorry about that. Yeah, so we have this asymptote. We have this -3. So we have a point for the center of gravity, and we have a direction. So you can think of that center of gravity line as showing you the tendency for that asymptote or that locus to move. So we know that the locus actually starts at -2. And now we have this vector that's telling us how that -2 is going to move. So that's how we can create those 2 points there. Any questions or comments there? So I'm just going to now modify this a little bit. So instead of using this function, let's just make it times s plus 3. So now we can see we are going to have, we'll have 3 poles. So at -1, -2, -3, we are still going to have the 1, 0. So one of those loci is going to start, so likely the -1 is going to point back towards that 0. And then we have 2 other loci starting at -2 and -3. And we have the center of gravity. And we should actually recalculate that center of gravity. So let's just duplicate this a bit. So for this case, where we have s plus 3, then our center of gravity is going to look like -1, -2, -3. And now we have 3 poles. So this is -6 over 2. So it's -3. Yeah. In fact, this one was right. Okay. So yeah, this one was -3 over 1. So that's fine. So here we have -6 over 2. So this is -3. So the same center of gravity. Yeah. And then for the angles, we've got now k equals, and we start from 0, and we're going to go up to, and it's 3 minus -1, which is sorry about that. Just giving everyone a minute to reconnect there. Okay, so we've got the 0, and then we said n minus m is 3 minus 1, which is 2. 2 minus 1 is the 1. So now we have the 1. And then, like we said before, that then gives us pi over 2 and 3 pi over 2. over 2 and 3 over 2, 3 over 2 pi. Right, so those are the two angles, and this time we can just do it quickly and just run that one. Right, so let's run this function. And by the way, as you watch it, you can see the roots being generated here. So it's working out your analytical form. And I've used a high resolution on these points for KP, so that's why it takes so long. Well, let's keep looking around this problem while we're waiting for that solution to show up. So these 2 points, those are pretty clear, right? So we've talked about all these, and so that's what we just applied, right? So those will help you with your start and end points and allocating the right pole to the right direction. And then you may also have the case where actually you don't have an asymptote pointing you in any particular direction. In some cases, you actually have, you might have the case where there isn't a clear asymptote, but there are what's called break-in and breakaway points. So you might have the case where your loci are traveling along the real axis and then they depart from the real axis, or they are coming out from some complex area and then they are rejoining into the real axis. So the locations of break-in and breakaway points, that's something we'll look at just now. Oof, this one's still not done. It took a long time to find all the solutions here. I didn't think this was such a difficult equation. Maybe I'm just going to try dropping the resolution for this. Oop, I think it's done. Okay, yeah. Okay, so again, ignore these 45-degree lines, and we can see here or starting point. We can see the -1 point here. So there is one locus starting at -1. There's another one starting at -2, and then yet another one starting at -3. And for the -1 locus, there is a tendency to move in towards the 0. And by the way, don't let the colors, the colors don't really mean anything. It's just when this is solved, it generates the solutions in this way. But this is just a locus of points. Each line there is not it's not a continuous function, right? That's why it's called a root locus plot. It's a locus of points. So when we talk about a locus, this is one locus. You know, so go rather by the lines and what they are doing rather than by trying to follow the color. So here we've got this locus which starts at the -1 and is moving in towards the 0. So if you like, we've used up that nice 0, right? The 0 tells us where we are going. So we've moved in like that. So that's one locus. Then for the other locus, we have these two starting points, right? For the other two loci, we've got -2 and -3. So those 2 points. And those two move in towards each other. And then we don't know what they do after that. But we have this point -3, and we know that we move off on pi by 2 and on 3 pi by 2. So we have -3, pi by 2, and 3 pi by 2. And so our locus starts moving in like this, but eventually it's going to be attracted in that way. And this locus also, it starts moving towards the other locus, and then it's going to be attracted down that way. And again, it's not clear to us that we can say, oh, this point then moved, when they met, that this one went that way and that one went that way. But anyway, we can say that there is a locus of points that does that, and then they tend off to start joining the asymptote after that. Right, so those are some clues about how to construct these root locus diagrams. Of course, it will occur to you that it still seems somewhat that there's still room for error. What if between the two, between all the features that we are able to extract, what if there are some there's some unexpected behavior in between? And yes, there's a lot more analysis you can do. There's a lot more that you can do in terms of finding features. So there are many clever techniques in complex analysis for finding more features and for refining your sketch of the root locus diagram. So all we can say is, number one, in the modern world today, we would just use a computer. So like I have done here, right? You can just write code and you can brute force just generate all the points for your control parameters. So you can get the complete control picture like that. So you either do that or you invest more time into complex analysis and looking for more features. Those are the two options. In terms of this course, it's not as if we are looking for very exotic functions that will necessitate us doing that. We don't have to go and look for all these other more complicated methods. It's good enough for us to emphasize these basic things. So starting and endpoints, asymptotes, that's going to be good enough for us for the types of functions we will encounter. Any questions or comments there? Right, now let's look at another example where we don't have these kinds of asymptotes. And so I'm looking for an example where we have break-in and breakout points. And again, we'll start with the example and come back to the development. But here, let's say we have a function like this, right? S plus 3, S plus 4 over S plus 1, S plus 2. Then if we go and graph this, and I've just copy pasted this in here, what we'll find, of course, our poles are here, and it's at -1 and -2, right? So again, our loci start at the poles, -1 and -2. So here's -1 and here's -2. So here we start on this blue line. The blue line actually starts here. So we travel up to this point, and then at this point we break out. So here we were traveling along the negative real axis, and then we broke out of the real axis and we loop around here and then travel in like so. And again, it's not a continuum. This is a locus of points. Right? But if we imagine starting here, we can think of that happening. And then the other one starts here at -2. And then that travels here, and it's not clear which one, but anyway, let's just say it's going down this way, travels through there, and then moves off in that direction. So here you can see we start here, and we start here, and we end here, and we end there. And if you look at these end values, so that's a -3 and that's a -4, right? And you can see those are the zeros. So this is an example of a case where your number of poles equals your number of zeros, and the asymptote, or rather the locus that starts at one point, it goes and it finds its way to the other end point in both cases. So here there's no center of gravity or anything like that. But if we just go on the principles we have so far, we will not be able to get anything like this, right? We would totally miss this important feature in the middle, right? And that's why it's also important to look at these so-called break-in and breakout points. And so the development for detecting that a breakout point exists, right? Because we could have said, well, if I'm starting here, maybe I've got one locus that goes straight in and ends here. And then if I'm starting out here, well, let's say I'm starting out here, I could draw two lines. I could draw a line from here to here, and I could draw another line from here to here. So I could claim that, well, it's actually all on the same negative real axis and be done with it. But that wouldn't be correct, right? So for us to detect whether this kind of feature does happen, right, that we are leaving this real axis at some point, we have to analyze the function a little better. And the development for that is shown here. So let's say, so this is where in the notes, usually the way this is taught, we're just told you work out the breakout points from this equation. So what I'm showing here is just the detail, the sort of motivation for where this expression comes from. So of course, we start out here with our with the equation we are trying to solve, right? All these loci are just solutions to this equation. And we know that we can separate our process function into a numerator and a denominator, n and d. And so if we substitute n over d here, and then rewrite this equation in terms of kp, right, we'll have that kp is minus 1 over gp, which is equal to minus d over n, so the inverse of that and minus times that, right? And then if we think about this, this is telling us that we are, if we are on the real axis, we are concerned about being on the real axis and then breaking out of that real axis. So that means we depart the real axis. So up to a certain point, we are just traveling along the real axis. And then when we reach a certain point, we'll move straight out from that real axis. And if you think about it, it means that we are moving along for different values of kp along a real number that's changing. And then at a certain point, that solution is going to move straight up. So if it's moving straight up, that means the real part is not changing anymore. It's only increasing in the imaginary part. So we can say that, well, let's convert our S value into two parts, into a real part and an imaginary part. And let's differentiate that value of Kp as we are traveling along. And we know that at the breakout point, the real part will stop changing and the imaginary part will take over. So if we differentiate just with respect to the real part, we'll get to 0 at that breakout point, right? At that breakout point, we're moving straight up. So it's not changing anymore in the real direction. So we can, if we let sigma be the real part of that S value, then the derivative Kp with respect to sigma will be 0 at that point of departure. And so if that is what we're looking for, then we can differentiate this expression. And of course, both these are functions of the real part of S, right? Both these are S functions, so both these will have real parts to them. And so if we differentiate this, we have to use the quotient rule of differentiation. So the quotient rule is that you differentiate the numerator and multiply by the denominator minus the derivative of the denominator multiplied by the numerator divided by the denominator squared. So that's just straightforward quotient rule differentiation. And then we said that's equal to 0, right? And again, that 0 is just because it means we are not moving in the real direction anymore. We are breaking out, so we are moving straight up, so the real part is not changing there. So if that's true, we can just multiply out this n squared, so get rid of that n squared, and then we can say, then clearly d dashed n equals n dashed d, right? So that's what we have here. And then we had said earlier also that actually more usually we will write our g function like this. We'll write it as a product of zeros and a product of poles. So n and d have this functional form. N has that functional form and d has that functional form. So if you take n, so all of that multiplied by the derivative of d with respect to sigma, where sigma is the real part of S, then you'll get some polynomial here. And then if you do the same thing on the other side, you take d and multiply by the derivative in n, then you'll get another polynomial. And I'll leave it to you as an exercise to show that it cancels nicely, leaving you with just that. Right, so that's where that comes from. So like I say, behind this kind of set of recipes or a set of relationships that we have, there is a lot of decent development. So you can motivate and justify all these expressions and all these methods. So anyway, that's how you work out the breakout points. And so if you take an expression like this, and yeah, I did it the kind of longhand way, n times d dashed and d times n dashed. So if you take your n, so the numerator here, so you can see I'm writing the numerator in terms of the real part of S, and then multiplied by the derivative of the denominator. So for the denominator, it's a product of two functions. So if you differentiate this, it's going to be, so this is going to be a 1, right? d sigma here is 1 multiplied by sigma plus 2. So 1 times sigma plus 2. And then if you differentiate here, it's 1 times sigma plus 1. So that's what we have there. So that's how you work that out on that side. And then similarly, on the other side, d derivative of n, that's what you get there. And so you basically solve this equation. And if you look at this, it's actually a cubic expression. So you have 3 roots, but anyway, the things that matter to us are the 2 breakout points. So this is actually a break-in point, and this is a breakout point. So here you are breaking out of the real axis, and here you are breaking back into it. Right, so the point is that if you look at this equation, and so if you work this out and you find that you have solutions to this, right? Looking at this equation, we can't dismiss it. We can't say, oh, we ended up with 0 equals 0. That means there are no solutions to this equation. That means there are no breakout points. So instead of that, we got a polynomial, and we know that if we solve that polynomial, it will give us some numbers. So it's telling us that there are going to be breakouts along the real axis there. So we know that such features exist. And then the next point is perhaps to try a couple of different KP values and figure out how that function is behaving near those features. Right, any questions or comments on that?
So, when you say try the KP values, do you mean just to directly sub it into the equation and just see? Because I get confused when I'm trying to plot on that axis, because that's where I got confused when I was trying to plot. I understood the starting points, ending points, But when it came to the breakout points, I get a bit confused on which one should go where, like whether it's breaking in or out.
Right. Yes, I do mean that. I do mean substituting some numbers for KP. So here I haven't actually shown a KP because I was just looking at plotting this function as it was. So in this case, if we solve this equation, we will get two numbers, which will be those break-in and breakout points. And then we could look at some small distances around those points. Or you could actually differentiate that function and test whether the real and imaginary parts are positive or negative. But anyway, we know it moves, yeah, we have to figure out whether it's moving towards or away from that point. So if we know a point here is basically a repulsor, if we see the derivative is pushing out here, and we see here the derivative is pushing in here. So one point is an attractor and the other point is a repulsor. Then we can say that as we move towards that point, we are moving away from here and in towards there. So that's what you would look at. You would take some small values for KP and then just out.
Can I put on the Ghostbusters movie?
A bit later. Come, go do your schoolwork.
I finished my schoolwork, Daddy.
Okay. Yeah, the joys of working at home, right? Yeah, so here you've got some indication of the movement around those breakthrough points, and so you can imagine how to connect those up. So if it's pushing out from the one point and pushing into the other, then that gives you an idea about the direction and how it all hangs together. Does that answer your question there?
Yes, thank you.
Okay. Any other questions or comments? Okay, so the best thing to do with understanding root locus plots is to do lots of examples, and you have a number of functions here. So you've got this tutorial 4 notebook. So you can try all these transfer functions and first try without using the code, right? Try to visualize how these functions will behave using all those principles. So just sketch out first what you think it should be, and then uncomment and run the code and see if the result agrees with what you've sketched there. So it does come down to those 6 principles. Those are quite useful for expressions of this level of complexity. Okay, so can we move on from root locus diagrams? Okay, now, of course, everything is in the set of videos, right? We do have these, everything we're about to talk about here is, I think it's in video 05, something like that, but we are going to talk now about this encirclement of this -1, -1, 0 point, because there are actually a number of different contributors before you get to, before you are able to rigorously say why this is true. So there is this logic thread, and yeah, I don't mind saying I am going to test on this, right? This is going to be a question in one of your assessments about tell me why it's true that we can, that if we encircle -1, 0, that there is instability, right? Because this is what the whole course comes to, right? Figuring out how important this -1, 0 point is, and how even closeness to that point tells us something about how safe that process is going to be. That's kind of one of the capstone concepts of this course. So, so it is there is a whole video on it, but here I've tried to summarize it down somewhat, and we are going to start with just establishing some of these basic principles first, and then we're going to talk through how to use these 3 basic facts to understand that what it's saying first of all, and then why that's true. So the first thing to look at is this so-called principle of the argument. I'm just going to open up the notes for that. Sorry, just looking for the page. Right, so yeah, principle of the argument. So this is saying that if you have some complex function with z zeros and p poles, if you so let's say you have some region. So imagine the complex plane, and we're actually going to imagine 2 complex planes. So imagine that there's an S plane and an F plane. So as you move around in S, F is going to do something, right? So we have some complex function. So we've got a function f equals f of S. And so in our S plane, we are free to pick any path in the S plane, right? And then in our F plane, as we move around in S, F is going to do something else, right? So for example, we can imagine drawing a circle in S. So we can let S vary, for example, around the origin. We can imagine drawing a circle in the S plane. And then on the F plane, as we pick different values on that circle, F is going to do something else, right? Maybe it's going to draw out a quadratic or a straight line or something. So just imagine there are these 2 different planes. And now we are saying that this function f, we are pretending now we don't know what this function is, right? So this function f, for this function f, there exists some zeros. So there are some values where f goes to 0, and there are some other values where f goes off to infinity. So as we pick values in the S plane, f is going to respond in some way. So if we pick a certain value in S, f might go down to 0. As we pick some other value in S, f might go off to infinity. And we are saying here that in some region in S, right, if we pick some region, and we can pick any region, right, it doesn't matter, whatever region we pick, if we encircle that region, so let's say it's a square, let's say we just chose arbitrarily some square, and we moved around the edges of that square, right, then as we move around those edges, if f goes through a rotation, right, if we look at what f does as we move around that square, if f goes around in, it doesn't have to be a circle, if f travels around its own contour, so maybe f goes around a triangle as we go around a square here. So as f goes around that triangle, we count the number of times it completes a triangle. So if we go 1 triangle, 2 triangle, 3 triangles, let's say, then we have n equals 3. So f has traveled around 3 times. And then that number 3 tells us the difference between the number of zeros and poles in the S-plane. So in the S-plane, inside of that square, there exists a certain number of zeros, so a certain number of S values where f goes to 0. And also inside that square, there exists a certain number of S values where f is going off to infinity. And now when we watched what f was doing, we saw we got three triangles, or just, so we got 3 enclosed contours, right? So that tells us that whatever number of zeros and poles we have, that the difference between them is going to be 3. So it might be there are 30 values that make f 0. If this is 3, then that means there are 27 poles. So this is a certain property, right? It's telling us if we count the number of encirclements or the number of enclosures, the number of times we enclose an area in F, that's the difference between the number of zeros and the number of poles in the S-plane. Right, so there is a proof in the notes about this, and it's in fact a surprisingly simple proof. In fact, it's done more by example here. So we take a simple example where we have 2 zeros and 1 pole, and we look at this closed contour. So we arbitrarily chose in the S-plane that we have the 2 zeros and the 1 pole, and we pick a point, and as we move around this space, you can see the angle here changes by 2 pi, the angle here changes by 2 pi, and here, remember the pole is in the denominator, so as we move around here, we subtract 2 pi. Right, so the response then is going to be that we are only going to see f going around here 2 times. So that's why this works, right? The zeros contribute a plus 2 pi, and the poles contribute a minus 2 pi. And when we say they contribute those angles, we mean that the output, we are always outputting a value for f. So f is going to encircle some other region by z minus p times. Okay, so shall we pause there? Please, any questions or comments on this specific point? Right, so that's the principle of the argument. So spend a bit of time just understanding what that's saying, right? So this one is about mapping in the F-plane, observing how many times we enclose a certain area there. And then that relates to the S-plane and the difference between the number of zeros and the number of poles. So let's take this part as a given. Then the second thing we have here is something we discussed right at the beginning. So we said that that if you have that when you have your function and you solve for the number of poles, right, or when you find the poles of your transfer function, then the pole of the transfer function is the time constant in your time domain function. So have a look in the notes about differential equations, and right, your solution is going to look like this, right? You are going to get a solution with time constants in it. So your lambda i's here are the time constants of your solution. And it turns out that the poles of your S domain are the time constants in your T domain. In fact, one of the easiest ways to believe that is just to look at this transformation table. Your transformation table here, right? If you look here, for example, right, in the time domain, right, remember this table for Laplace transformations. So in your time domain, you've got e to the minus bt, so your time constant is b here. If you Laplace transform that, you will get 1 over s plus b. So clearly here, your pole is minus b, and you can see minus b is the time constant in the time domain. Right, so that's the second important principle, that the poles of your S domain are the time constants of your T domain. Any questions or comments on that point? Right, and then if you look at the development of your closed loop transfer functions, I think that's in notes 4. You'll see that when you close the loop, right, we spend a fair bit of time looking at open loop transfer functions, and then when you connected the output from your controller to the input so that you were actually implementing control, it turned out that we always got this factor of 1 plus the open loop transfer function in the denominator. Right, so have a look at this part of it. You'll find that we always have your closed loop transfer function having a denominator that has this factor of 1 plus g open loop, right? So these are the, if you like, the three starting point facts. And then we want to know, how does this imply that -1, 0 is important? And if we look at it here, so we are saying that our closed loop transfer function has this in the denominator. So that means that any solutions to this, right, any solutions to 1 plus g open loop equals 0, those S values must be poles of the closed loop transfer function. So those are values of S where the closed loop function goes to 0, right? If this is in the denominator, if g open loop is -1, then we'll have a 0 in the denominator. So the closed loop function goes off to infinity. So it's a pole, right? Then the poles of, we just said that the poles of the closed loop transfer function are the time constants. So the poles of that are going to show up in lambda in our time domain solution. And so that means if lambda has any real part, then y of t is going to go off to infinity, right? Because we are going to have e to the positive number times t. And t is time. We can't stop time. Time is going to flow forward. And so as time increases, if you have a positive part there, that term is going to go off to infinity. And so our response goes off to infinity. So that's our definition of instability, right? Our output shoots off to infinity. So we don't want lambda to have a positive real part. So that tells us that we want then that the poles of the closed loop must only have negative real parts, right? That's what we want. And be careful when I'm saying must here, it doesn't mean that's a rule or anything. I mean, we want it to have negative real parts because we want stability. So we have just said, however, that the poles of G closed loop are the roots of 1 plus G open loop. So the zeros of 1 plus G open loop are the, so let's carry on. We said we want negative real parts for the time constants, and the time constants are the solutions of this equation. So, so now let's think about finding those zeros. So we want to figure out, do we have any positive real parts? And to answer that, we can now think about using this, this interesting principle of the argument theorem. So to find out if we have any positive real parts in the complex plane, we can imagine a region that goes around the entire right-hand plane. So of course, you've got your real axis and your real axis and your imaginary axis. So your entire right-hand plane, we want to look at that whole region, and we want to try and use this this principle of the argument theorem to figure out if there are any poles in there. So we want to know, are there any poles in that region? Because the moment we have poles in the right-hand plane, then that means we will have a positive part here, right? So that's the definition of stability. So to figure that out, we are going to draw a boundary around that whole region. And we'll talk just now about how to draw that boundary, but for now, let's just say we can somehow do it, right? So we draw a boundary around the entire right-hand plane, and then we travel around the edges of that boundary. So even though it's an open boundary, we somehow claim that we are able, that there exists such a thing as an edge, and we'll be traveling around that edge. And so if we travel around that edge, then, so that's in the S-plane, right? We are traveling around the edge of the entire right-hand plane in the S-plane. And then we can watch what's happening in our function in our F-plane. So if our F-plane gives us some shape, and if it's encircling that shape a certain number of times, then that number of times tells us the difference between the zeros and the poles in that right-hand plane, right? Now, one additional constraint we can come up with is to say that, well, if we have a process that's inherently stable, so let's say we know that we don't have any poles in the right-hand plane for the transfer function itself, right? So let's say we have a process that's inherently stable. That means it won't have, to begin with, any poles in the right-hand plane. So we know that P is 0. If that's the case, then the number of encirclements that we see in the F-plane will equal the number of zeros in the right-hand plane, right? And that's so that's the first bit of logic. So there are no poles, and then we are looking at whether we are encircling a point here. Now, so if we encircle the origin n times, right? And I think I didn't say origin when I was talking about principle of the argument, but that's what I was supposed to say. We look at the number of encirclements of the origin. Now, that's true in general when using the principle of the argument. However, in this case, when we are not interested in encirclement, we are not interested in just this function. If our function is actually 1 plus that function, then it's not the origin. If we look at encirclements of -1, 0 for G open loop. So once more, this is the function. We want to know if this function encircles the origin. So you can, of course, plot that function and look for encirclements of that function of the origin. Alternatively, you could say, well, why don't I just work with G open loop and look instead at encirclements of -1, 0. So you travel around the right-hand plane in the S domain, and then you observe encirclements of -1, 0. If you get any encirclements of -1, 0, then that means you do have a 0 for your for this function in the right-hand plane. Remember, we are looking specifically at the right-hand plane. So if we have a 0 in that right-hand plane, then that means we have a pole in the closed loop in the right-hand plane, which means it's going to be unstable. So that's the motivation for looking at encirclement of -1, 0. Any questions or comments on that? Right, so follow this line. I don't fully expect that from this audio explanation that all the pieces hang together. And it's useful to draw your own diagrams and try and put things together. But from these basic principles and from these choices, we are able to see why encirclement of -1, 0 means that there has to be zeros of G open loop, which means there are poles of G closed loop in the positive right-hand plane. And then this is just a comment about encircling that right-hand plane. So we can think about 3 different paths. So if we imagine the origin here, then if you look at S going straight up, so we let S equal I omega. So it's moving purely on the imaginary axis, and omega is going from 0 off to infinity. And then we are looking at S equals, in polar form, we are looking at S. So we let R go off to infinity again, but we let the angle swing around. So from pi by 2, and okay, I need to draw it this way. So from pi by 2, it's going to circle around. So here's your right-hand plane. And so we go straight up off to infinity, and then we circle around the entire right-hand plane. That's letting R go off to infinity. So we are down here now, and then we come straight back up. So here S equals I omega, where this time we are going from -infinity to 0. So I think you'll agree then that you start from the origin, go straight up, circle right around, and then comes back up to that point. That means you've fully encircled the right-hand plane. So that's how we can define our path encircling that plane. And then we can think about, then we look for number of zeros and poles and all the rest of it. Here, now that's strictly speaking, if we follow all the steps that were mentioned here, right? Now we can think about simplifying that further. So let's think about whether we really need this step, right? So we know that in principle we have to go around all the contours of the entire right-hand plane. But is it possible that we don't need to look at some parts of this? So first off, or second really, in this step, R is going off to infinity. So S has an infinite value. The magnitude of S is infinity along this part of the plane. Now, if we look at our transfer function, we have m zeros and n poles here. And we said for physically realizable systems that m is less than n. So that means you have a higher order of S in the denominator than in the numerator. So you might have S squared up here and S cubed down there, right? Your order up here is always more than your order down there. So if that's the case, then as the magnitude of S increases, your denominator is going to increase much faster than your numerator. So if your denominator is increasing faster, then your value of G is going down, right? So if R then is going off to infinity, then G is going towards 0. So that means you are staying away from the -1, 0 point. Instead, you've been collapsed down to the origin. So that means along this path, so even though S is traversing this massive region, on the G graph, it's actually just contracted into a single point at the origin. So this part of the travel is not going to get us anywhere close to -1, 0. So we can say we don't really need to go there. We don't, in terms of investigating S values, we can just ignore this part of the path. So G, we are looking for encirclements of -1, 0. Actually here, G is just stuck at 0. So we don't have to worry about that part. Here, we are going from -infinity up back to the origin. Now, one thing we know about these plots is that they will give us complex conjugates. So here we are looking at positive I omega. This is negative I omega. And so G is going to respond in complex conjugates. So if we have a complex conjugate, so G might be traveling around in this direction in the first part. And then in the second part, it will just travel in on the complex conjugate to that. So it's not going to give us additional encirclements. So because of the property of complex conjugates, we can say these two, 1 and 3, are going to give us the same information. So we don't have to commit to number 3 either. So it becomes, we just need to do this part. We might as well just look at S equals I omega and let omega go from 0 to infinity. And as we vary S like that, if we see any encirclements of -1, 0 in G, then we know that there's instability. Right, so when you first approach the section and you see for some reason now we've chosen S equals I omega, this is the reason, right? Just looking at S equals I omega, that gives us all the information we need about how close G is going to come to -1, 0. Any questions or comments on that? Okay, so that's, if you like, the logic of the whole course, right? That establishes for us that method. And then, do we have time for an example? Maybe you can use the reactions and tell me if I can go through this example or if we're really out of time. Okay, thanks, Karen. Okay, so let's look at this example. Thanks, Kieran. We've got here this transfer function, 10 times s plus 1 over 1,000 times 2s plus 1 over 50, all of that over s plus 1 over 10 all squared. So this is our transfer function, and we are asked to sketch the Bode diagram. And if we apply p control, what value of that proportional controller gives us the 2 decibel line. So let's just talk about the Bode diagram for now. So this is our function. We know that to construct the Bode diagram, we need the log modulus as a function of the frequency. And we also need the angle as a function of frequency. So for the log modulus, the definition is 20 log 10 of the magnitude of G. And so we just substitute the function G in here. And we can see that we have the product of several terms, and we can, of course, use the property of logs to break this down. So instead of having this one big group, we can break this down into the product of, first we can just extract the constant. So there's a 10 in front here. So we can just write 20 log 10 out in front here. So log 10, by the way, of course, that's a 1. So that's 20. And then we can say 20 log 10 of I omega plus 1 over 1,000. And by the way, these square brackets throughout should be magnitude signs, okay? So just read these as magnitude signs, please. So there's that factor, and then of course the next factor, and then for the denominator, of course we can read that as raised to the power -2, so or -1 times that squared, and so with the minus in front here, we've got that term. And then what do I do here? Then here I move that 2 out in front, so it looks like that. And then here we are trying to get this form, right? We want to get rid of this coefficient here. It's going to help us with our plotting. So we always want the form omega plus something. So that's what we want to get here. So we split off the 2 here. And so when you factor out 2, then you also have to factor the 2 out here. So this becomes 1 over 100, or another way to say it is 2 times that 1 over 100 is 1 over 50. This, not much was done. And then here now, this 2, this is 20 log 2 plus 20 log I omega plus 1 over 100. So the 20 log 2 I'm grouping in here with the 20 log 10. So by writing 10 times 2, I'm just grouping that out here, right? And then the rest is just the same. So now we don't have the 2 in this term anymore. And so it's all written in this form. And if you look at your Bode plotting, I'm just going to take some simple functions here. So for tutorial 5, excuse me, for tutorial 5, we have all these, we have this code for doing all our Bode diagram plotting. So we just specified the function down here. So let's just look at, let's look at 1 over s plus 1. Or let's just look at s plus 1 to begin with. So it's still running. So here's the Bode diagram. If we brute force go and plot it, so you can see it's on 0 here, and then around this value of 0, it takes off. Not 0, this is a 1. Around this value of 1, it takes off like this. Now let's modify that a bit. Let's make this 1 over 10. So that's a 0. Okay, so write it as 0.1. When we run this, and I'm just going to drop this so it runs a bit faster. So we've changed it now to 0.1, and you can see now this point of inflection is at 0.1. So it was 0, it reaches minus 20. It reaches 0.1, and then it shoots off like that. And you can let's make this 1 times 10 to the minus 3. And you can see now at 1 times 10 to the minus 3, the inflection point is like that. So your intercept, if you like, so if you produce this asymptote back here and this flat line back here, it's going to intersect at this value. So as long as you have S in this form, and by the way, in the code, I make the substitution S equals I omega. So if you have I omega plus some constant, then that constant is going to be the point where we depart from. So the function will curve around that point and continue on that asymptote. So that gives you a nice point here. So when you're trying to sketch this, you can say, okay, up to that point, it's a flat line. And then beyond that point, it's a straight line. So you can draw straight lines here and then just add a small curve in there, and that helps you to draw this. So that tells you where the point is. The other thing to notice is the gradient at which that's increasing. So here, if you look at a factor of 10, right here it's 0.1 and that's 1, so that's a factor of 10. For a factor of 10 change in omega, we are going to get a 20 here in delta L. So I'm trying to say delta L is 20 when delta omega is a factor of 10, right? So that helps us in figuring out how to plot these lines. So when we look at this, we can say, yes, for this part of the Bode plot, it's going to, there's going to be that inflection point at 1 over 1,000. And here I've got straight an I omega with the 20. So it's going to be a flat line up to 1 over 1,000. And then after that, it's going to be 20 per factor of 10. So we know how to add this contribution. This contribution is a constant, right? So we can just work out 20 log 10 of 20. So that's going to be a constant. And then if we add this factor, then we'll say we'll move along that constant until it's 1 over 1,000, and then it's going to shift up by 20 per factor of 10. And so that will be up to 1,000. Then when we reach 1 over 100, you can see a second inflection will occur. And that's going to add an additional 20 per 10, per factor of 10. So it's going to rise even more sharply then, right? And in fact, let's plot that so we can see this. So let's multiply here by s plus 0.01. And yeah, it's a bit too curved to see very well, but yeah, let's see. 1 over 100. Let's try zooming in a bit. That's not going to help. It's okay. Let's try and move it out a bit further. Let's make it 10 to the minus 4 and 1. So 10 to the minus 4. 1. Right, so I think that's a bit clearer. So here you can see at 10 to the minus 4, we start to get that 20 per factor of 10. And then when we reach the 1, you can see the gradient becomes even more sharp. Now you can see it's 40, right? 80 minus 40 here. So it's 40 per factor of 10. So the gradient has doubled there. So that's the result of having 2 of those factors together. So that's what we have when we multiply those 2. And then if you have terms in the denominator, and here this is 1 over 10. So let's just do it here. So if you divide by, and let's make this at 100, s plus 100, and let's square this denominator. So we might anticipate that, well, from the first 2 terms, we've doubled the gradient. And from this term, it's going to reduce that gradient by 2 orders. So it should flatline actually at the end. And yeah, I need to extend this further to see that. So let's use while we're waiting for that, let's keep talking here. So that's going to be the contribution from there. For this part, yeah, we've grouped out this term, so we got an I omega. So so the fact that this was actually a 2 in here, we managed to get rid of that 2, and what that 2 will do is shift the original intercept. Right, so when you see factors with the omega, you want to move that away from your function. You want to keep your function linear. Well, not just linear. You want to keep it with omega itself. You don't want to multiply that by any factor, and you can easily get rid of any factors just in this way by splitting it off and moving it into the intercept. So yeah, it looks like I need to go even further, but it's basically flattening out. You can see the curve sort of bending over that way. So it's, yeah, we go up with that higher factor, and then it trails off. It flattens out after that because of the influence of the denominator. Any questions or comments so far? Okay, so basically what I'm trying to say here is for the Bode plots, it's a matter of breaking down our complicated transfer function into all these terms, and then we can just draw this crossover frequency point and this gradient. So we can draw two lines, and then we can just add all those lines together to figure out how the overall process is going to behave. So that's the L part of it. There is also the angled side of it. So a Bode plot is broken into your log modulus and then your argument of your complex number. And the same approach applies here. So if you have the argument of two numbers, I've written a brief motivation for that. The argument of two numbers, of the product of two numbers, is equal to the sum of the arguments of the individual numbers. So that's of course based on that you can translate these two complex numbers into their product in the polar form. So when you multiply them in polar coordinates, you'll end up just adding the angles together. So when you multiply these two exponentials, those angles just add together. And so the argument of this is just going to be θ1 plus θ2, which is just the sum of the arguments of the two numbers. Right, so a very similar approach then to plotting out the angles there. So again, please do go ahead and for all these, for that sort of gallery of functions, go ahead and plot out your Bode diagrams, right? So practice drawing your Bode diagrams quickly. So of course, Bode diagrams, those commonly occur in this type of course. And so practice doing them, be able to draw them quickly and easily. Then you won't lose time on that. Then the last important one to look at is the Nichols chart. So if you have your Bode diagram plotted, just going here, yeah. Am I looking at the right? So here. So if you have your Bode diagram drawn out, what we want to do next is take these two diagrams and convert them to one curve on the so-called Nichols chart. So the Nichols chart is a plot of your open loop log modulus and angle. So instead of plotting L and theta as functions of omega, if we instead regard omega as a parameter along a line in L and theta, then we can select values of omega. So for instance, if we choose 10 to the minus 6, we can see here L is minus 160 and theta is about minus 360. So we would find that point here. Here's minus 360 and minus 160. So that defines that point. And then we pick another value, let's say 10 to the minus 4. So we can see L is that value and theta is that value. And so that defines another point. And so we just keep picking omega values, and then that draws out this curve for us. And then you can't easily see it here, but there are examples in the notes where there's this 2 decibel line, and that's considered a desirable line. It gives us a good performance for controllers because it doesn't have such sharp oscillations, but at the same time, it gives us a fairly good response of the system. So the 2 decibel line is a desirable thing, and by manipulating Kp and tau I, this whole curve can shift until it's a tangent to the 2 decibel line, and then we know that we have a good controller. So I think we do need another session just to have some practice with that, but that's the point of drawing these things, right? You draw your Bode diagram first. Once you've got your Bode diagram drawn, you can take that and translate it into a L and theta on this plane, then that gives you a curve here. And then as you adjust Kp and tau I and tau d, that will move this curve around on this plane. And you look to move that curve till it's tangent with the 2 decibel line. Okay, any questions or comments on that? Okay, if not, that's about it from me for today. Like I say, please email me with any questions that you want me to go through in more detail. Yeah, we'll set up another time for that. Okay, thanks everyone. Bye then.